This is the topic we are gonna learn. So we know what a subgroup is, and we know how to show that given a given set is a subgroup. There is a special kind of subgroups that has some property, and we will call this special kind normal subgroups. The property of normal subgroups allow us to define factor groups, define new groups from old ones. So our goal in this section and in the coming section is to create a new group. Now here it says if possible. So the idea, we start with a group G and take a subgroup of it, which is K. Now using this K, we might or might not be able to define a new subgroup using the G and the K. If this K is normal subgroup, then we can define a new group, and which we will call factor group or quotient group. So we must have a subgroup K that enjoys some property, and we will call such kind of groups normal subgroup. Okay, and the new group we will create consists of cosets. So the idea again, we have a group G and the subgroup K inside it that enjoys some property K, which we call normal subgroup. And then what we do, we take the cosets of K. We have seen the cosets of K are subsets from G. Now these cosets will be the elements of the new groups that we are gonna define. And actually we have done such a thing before when we worked with the group G to be the group of integers Z, and the subgroup was 5Z or 6Z. And what we will do, we will generalize this concept. Let me write this here. It will be a good idea if we start from something we know and then we go to generalize. If we choose the subgroup K to be 6Z, now we made the right cosset or the left cosset, because left adding from the right or the left inside this group Z does not matter because this group is abelian. But let's keep it as a right cosset. So you remember what we have done, 6Z plus 0, which is 6Z itself, 6Z plus 1, and we have studied these things in very detailed manner. 6Z plus 3. So all these are the left cosets of 6Z, 6Z plus 5. Six Z plus 5, and we denoted this by Zn, and then actually we used different notations for it. We used 1 for this, 0 for this, 1 for that, 2 for this, and 3 here, 4 for that, and 5. And then we got a group which we called Zn. But originally we got this group Zn out of using the subgroup 6Z. So we had these cosets in here, and we defined addition on them, and then we obtained a new group sorry, that we will call this group, we will call it G factor K. In our case here it is Z factor 6Z, and we will work out to show this is what we mean by Z6. This is what we are going to learn in this section and the section that comes after. And the techniques that we have done in that section, which is modular arithmetic, will be generalized now in this section. Okay, so to define normal subgroups, let's go step by step. Now assume we have a subgroup K. Now we know what does it mean for AB to EB equals. Remember that A equals congruent to B modulo K in general, modulo K. So the definition says this is true if and only if A B inverse belongs to K. This is in the case the operation is multiplication, and in the case the operation is addition, we will write A minus B, or A minus B belongs to K. Okay, now the question here, if I have A and B are equal, let me say modulo K, and also C and D equal modulo K, what happens if I add or multiply A times C? Would that equal multiplying B times D, as we have here? And we will call this property star. Okay, this is not always true, huh? It is true when we worked with the congruence classes inside Z, the ones we have seen above there, modulo 6. But is that true for any subgroup K? The answer is no. This is true for special kind of subgroups, which we will call normal subgroup. And this property here is what we need to go and define factor group. Okay? Okay, so let's work on that. So the idea again, let me emphasize it. A equals B modulo K, C equals D modulo K, then AC equals BD modulo K. And whenever we have addition, the operation is addition, then we will have that. This is the question, when we will have such a property. What kind of subgroups allow us to do such a thing? Okay, so let's go for it. We have defined right coset as we have seen before. K is to the A is to the right of K, so we said right coset, and the definition is here. Similarly, left coset is defined in similar way, but we multiply A to the left of K. We might be in a group which is not abelian, then this multiplication matters. We multiply A from the right of every element of K, or from the left. The result might be different. Okay, so let us see. This is an example here. If we choose K to be the subgroup R0 and V, in case this is not clear, let me write them here. R0, which is the identity, and V of D4. This is a subgroup of D4. And V is a reflection about the line y equal negative x. Anyway, we assume we know that the multiplication table of D4, what is it? So let's compute the right coset. So now we are choosing K to be this subgroup, and we want to compute the right coset of K, but using D, multiplying it by T. So we can compute the right coset or left coset of the subgroup using any element from the group. So here we would choose K. So that means we will multiply the elements of K. Here we choose D, I mean. Did I say K? Here we choose D. So we will multiply any element with of K, R0 and V, with D. And multiplication here means composition. Now if we use the table R0 compose D is D, here we go, and V, we start here, V compose D is R3, and this is the result. Now what if we multiply D to the left of K? So we start D here, T times R0 is R0, and then D times V, where is V? Here we go, is R1. Okay, so we got KD does not equal DK. So the right coset and the left coset of the same element are not equal. They might not be equal and they might be equal. Okay, now the normal subgroups that we are going to define will stipulate, will force this to equal. We will say K or N, we will use letter N, is a normal subgroup if the equality here happens. Okay. Now I left something, I want to go back to it. Okay, we will see now that the operation star does not necessarily hold, and here we are choosing K to be this subgroup of D4, the one we have already chose. Let me write it here. It is R0 and V. R0 and V. Okay, now here we will show that R1 and T are congruent modulo K. R2 and H are congruent modulo K. But once we multiply R1 and R2 and multiply H and T, then we get no equality, which means the property star is not holding. Now, to show this is true, that means we need to show that R1 T inverse belongs to K. But what is T inverse? What do we need to multiply T with so that we get the identity? Actually, T is a reflection, so it is its own inverse. Now if I go here, I find T here, go all the way, I find the identity is here, multiply T by T itself. So that means T is equals to its inverse. That means now I need to show that R1 multiplied by T belongs to K. And is that true? What is R1 multiplied by T? Now the multiplication here, I mean composition. So we go to R1 here, go all the way till we reach T, and here it is. R1 compose T is V. So this is true, since R1 multiplied by T is V, and that belongs to K. V belongs to K. It is here. Now to show this thing, similarly, R2, we need to show that R2 H inverse belong to K. H is a reflection, so it is its own inverse. So that means I need to multiply R2 by H and see whether it is in K or not. We go here, R2 times H is V again, and this is true, since R2 times H equals V, which belongs to K. Okay, now we need to show these two things are not congruent modulo K, and to do so we need to show that R1 R2, so I'm using composition here, I'm deleting the little circle, the composition, so I'm using a notation of multiplication. So I need to show that R1 R2 multiplied by the inverse of TH does not belong to K. But that means what is the inverse R1 R2? The inverse of TH is H inverse T inverse. Okay, so but H inverse equals H, and same thing for T. So I need to show this multiplication does not belong to T. I will leave it for you to do. Actually, multiply these two things first. We are in a group, so it is associative. And multiply these things, you get two elements. Multiply them, you will get element which is not in K. Remember that the elements of K are R0 and V only. And the multiplication here shall not be one of these. So this shows that there are some groups, subgroups where property star does not hold. Okay, so good. So we have seen computed left cassette and right cassette, and talked about the property star. What else we need to do? Okay, the example we have just seen for computing the right cassette and left cassette showed that the left cassette and right cassette of K, for using the same element D, these two cassettes are not equal. But here we will take another subgroup of D4, which we call N, where the left cassette always equals the right cassette. And this is the kind of subgroups that we are going to define. So let N be this subgroup of D4, R0, R1, R2, and R3. These are the rotations of the square. They make subgroups, right? If you have two rotations and compose them, then the result will be one of the rotations in there. Okay, now, and let's choose V here to make right cassette and left cassette of N. Okay, so we will make the right cassette, multiply N by V from the right, and here multiply N by V from the left. So that means we will multiply V from the right by every element of N by R0, R1, R2, R3, and then do the computation. We get V D H T. Notice that the multiplication of R0V give us, okay, give us, and this is not the one I want. Note that here, let me do that again. R1 compose V will give us D, okay? But here, V compose R1 give us T. Agree? Okay. Remember this. What for? Now, after the computations, now here Vn is multiplying n, every element of n from the left by V will give us this set. Now notice these two sets are equal. The elements are listed in different order, but they are equal. The two sets here are equal. Left cassette and the right cassettes are equal. Okay, now let me go back to what I wrote here. That does not necessarily means, let me write this and we will see it again. This equality does not necessarily mean that V commutes with every element of n. Okay, so having NV equals Vn, we are not saying here V is commuting with every element of n. No. And an evidence here is what we have already seen. R1V is D, but VR1 is not D. So let me write that. R1 compose V is not equal to V compose R1. So having this equality here does not necessarily mean the elements commutes, okay? But the left cassette is equal to the right cassette. Done? Okay. Now, what we have achieved here, we have chosen this subgroup N and computed the coset of N using the element V. What about the coset of N using the other elements of D? R0, R1, R2, R3, H, D, and T. Here you go. Now, if you repeat this process, compute the left coset and the right coset using any other element of D. For example, for R0, this is trivial because composing R0 with any element, R0 computes with every element. So we will get the equality. Okay? But the opposite is not true. If the element commutes with every element of N, then left coset equals the right coset. But having the left coset of some element with N equals the right coset of that element with N, then that does not mean that element commutes with elements of N, as we have seen here. Okay? Now, go back and compute the coset of using R1, left coset and right coset, and they will come out to be equal. Same thing for left coset and right coset of R2 and R3. Here the V we have computed already. Compute the left coset and right coset using T and using H and using D. Do all these. Do them all. You must make sure these left and right coset, they are all equal. Actually, once we learn more ahead in the next section, there will be some other way to prove this without going to do all these explicit computations. But you need now to go and do them in details. Maybe you do one of them or two of them, and then you get the idea, and then you are done. Okay. So what we have achieved so far, property star does not necessarily hold for all subgroups. We have computed some cosets left and right that are not equal for subgroup K, but now we have a subgroup N where left coset and right coset are equal using any element of the group. Okay, so what's going on here? So this property for having left coset and right coset of N to be equal, where these cosets are computed using any element, will motivate us to define the basic component of our lesson today, which is normal subgroup. So a subgroup N of G is called normal if NA equals AN for every element in the group. So having a subgroup N, okay, taking any element from the group, compute the left coset for that element, right coset, sorry, and compute the left coset of that element. If they are all equal, then we will say N is normal. So we are assuming it is subgroup, then it is normal subgroup of G. So this is the definition of normal subgroup. Okay. Now, after we define the normal subgroup, we will work out some examples on normal subgroups. Intuitively, every subgroup of a abelian group is normal. If we have a abelian group, that means all elements commute with each other. That means multiplication from the left or from the right will give the same result. That means left coset and right coset are the same. So if N is a subgroup of a abelian group G and A is any element, then N times A equals A times N for every N in the subgroup. And that means NA is the same as AN, the right coset is the same as left coset is the same as the right coset. So every subgroup of an abelian group is normal subgroup. Okay. Now in D4 we have seen a group K which was not normal. So if we go back to the group we have seen above there, it will be a good idea. If I go back, we have seen what is the definition of normal subgroups, and we have two examples already in hand, and then let's go to these two examples and see which one was a group, and which one normal subgroup, and which one was not. So I mean, we are here at this subgroup K, and we noticed so this subgroup here, this K, and we noticed that the left cassette and right cassette for some element D are not equal. Then we will say K is not a normal. It is a subgroup, but it's not a normal subgroup of D4. Okay, now you see, when we work examples with subgroups and ask whether they are normal or no, we avoid the groups that are abelian, because we know any subgroup of abelian group is normal. So that's why we are working in D4. We chose a group which is not normal, which not is abelian. Okay, now in here, the left cassette and right cassette of all elements, the left cassette and right cassette of n using any element in the group rows equal, then we will say n, this subgroup here, the one above here, which is consists of the rotations of the square, and is a normal subgroup of D4. Now notice here, to say a subgroup is not normal, it was sufficient to have one element whose left cassette and right cassette with that subgroup are not equal. Then we say it is not normal, then we are done. But to say a subgroup is normal, then we have to check the left cassette and right cassette of every element in the group with that subgroup, as we have done here. We have checked left cassette and right cassette for all elements. Okay, but fortunately, this is not the way that we are gonna prove whether a given subgroup is normal or not, because we will learn some characterization of normal subgroups, as we will see in the coming theorems. Okay, now again here we have one normal. Okay, every abelian group, subgroup of every abelian group is normal. See, this example chooses another subgroup of D4, which is M, consists of R0 and R2. Now, if you want to understand this correctly, understanding this idea, R0 is leaving the square as it is. Okay, so we have a square like that. If you remember how we defined the D4, we had a square right like this, and this was 1, 2, 3, 4. And now R0 is leaving as it is. R2 is rotating 100 degrees. Okay, so when you rotate 100 degrees, this is R2. When you rotate one more 100 degrees one other time, this is R2 square, and then you go back to where you started, which is R0. So R square is identity. So this is a subgroup. Okay, now the question, it is normal subgroup or no? Simply we will check, but the idea here is so quick. D4 has 8 elements, right? So we have to compute the left cassette and right cassette of every one of these elements. So we have to compute 8 left cassettes and 8 right cassettes, same thing as we have done with n. But here, remember that this subgroup was special for us, R0 and R2, and we have seen it when we were asked to find the center of the group D4. Do you remember what the center means? Given a group, the center of that group consists of elements from inside that group, such that these elements compute with all elements of G. And the center of D4 we computed already to be R0 and R2. So R0 and R2, each one of them computes with every element of D. What this statement says here. Now R0 is the identity. This is direct. What's about R2? R2 commutes with every element A, where A belongs to D4, because we know it is from the center, and we prove that using the multiplication table of D4. And because R2 commutes with every element and R0 commutes with every element, so multiplying them by the left and the right does not matter. So AM, MA and AM will be equal for all elements in D4, and therefore M is normal. Now this example here generalizes what's up there, so this is a special case of that. I mean, about the above example is a special case of the below example. The example in below says that if we choose the center, which we know it is a subgroup, if we choose the center of the group G, so center is redefined here, all elements from the group G, such that these elements commute with every other element in the group. Then CA equals AC for every C in the center. Any element C from the center commutes with all elements A from G. And that means the left cassette, the right cassette of Z, of G, equals the left cassette, always. And therefore, the center of the group is always normal. The center of any group, regardless this group is abelian or not, is always normal. Okay. Now, in this example, we have already explained the idea. It says that if we have the left cassette and the right cassette of some element to be equal, that does not imply that N commutes with all elements, A commutes with all elements of N. No, that does not imply that. And we have seen an example actually. In particular, when we chose N, here is the example I talked about already. NV equals Vn, but R3 is from N. Okay? And we see here R3 V equals T, and V compose R3 equals D, and these are not equal. So the left cassette and right cassette, if N with respect to V made by V are equal, but V does not compute with elements of N. Okay? So having the left cassette and right cassette being equal does not necessarily mean the representative, the element A, computes with all elements of N. Okay. So having a left cassette and the right cassette does not necessarily mean the element commutes. Here we go. But now, nevertheless, there is some sense of commutativity here. A weak version of commutativity. It is true that an A does not equal AN, but notice that if N is an element of the subgroup and A is an element of the group, then for some N1 and N2, see what we have. Multiply small n by A from the right, and because we are saying NA equals AN, then small n times A shall belong to A multiplied by capital N, which means that here, see? Here. And small n times A belongs to capital N times A. But capital N times A, this one here is here again, equals A times N. So small n times A equals A times N1 for some N1 belongs to capital N. So let me rewrite that here in blue. N, small n times A belongs to capital N times A. Okay, this is natural. But capital N times A is the same as A times capital N. So what we got here? We got this belongs to that. But how the elements of these things look like here? They are small a times some element of n. So we got now, we moved from here to here. Now same thing applies here. A times small n, here we go, belongs to a capital N. But a capital N is the same as capital N times a. So we will have a times small n equals n2 times a for some n2 in the group. So some sense of commutativity has been achieved here, and this technique we will need it to understand the proofs of two theorems that we will see now. So I want to erase that and rewrite. See what happens now. Elements of n came out to be one time at the left and another time at the right, and so we changed the position of a, right? And here we changed the position of a again, and we changed the positions of the elements of n. But the elements of n here might not be equal. So this is some weak version of commutativity, okay? And it is a good that we notice this, because we will use it to prove some theorems. Okay, so it was, for this example, we have seen that the left coset of V is the same as the right coset, but V does not commute with R3, right? We have seen R3 compose V does not equal V compose R3, and that kind of not feeling well. We always like commutativity, but it might not happen. But in the case of normal subgroups, left coset equal right coset, we can replace that with weaker version of normality. See here, R3V does not equal VR3, but R3V equals V times some another element of n. So R3V equals V, but R1, VR1. So it is kind of commutativity in here. And this example follows the above discussion. Okay, now this theorem says that if we have a group, subgroup which is normal, a subgroup N, which is normal subgroup of G, then the property star holds. If A and B are congruent modulo N, C and D are congruent modulo N, then A times C is congruent to B times D modulo N. And remember, the notation here is operation is multiplication. If it is addition, then we will say A plus Z equals B plus D modulo N. Now, so this is this theorem is about property star that we started with, and says this theorem says property star holds for sure when the subgroups you are working with is normal subgroup, and this gives an alternate this part shall not be here now. This part comes with the theorem that comes after this. So let's prove this theorem here. We will prove it somewhere. So now this theorem will tell us that a special case where property star holds. Remember, property star that we started with will hold if N is a normal subgroup. If A equals B modulo N and C equals D modulo N, then AC equals BD modulo N. And remember, if the operation is addition, we will have A plus B, A plus C equals B plus D modulo M. Okay, so let us prove this theorem. Okay, now before we start the proof, let's understand what we want to show. Let's characterize what we want to show. This is the way you work with exercises in algebra or proofs in algebra in general. In fact, in mathematics in general, but in very particular case in algebra as a very technical topic. So to show this, what we need to do, we need to show, let me explain. To show that, we will show that AC times BD inverse belongs to N, correct? And that means AC D inverse B inverse belongs to N. If we can do that, then we are done. Okay, what information we have from this here? We have AB inverse belongs to N, and from this here, and this all one line, we have CD inverse belongs to N. So can we reach the green out of the blue? Can we do that? And remember, we need to use that N is normal subgroup. So we also have that N is normal. So left cassette equals right cassette. But which left and right cassette we want to use? Let's use this and start with that and show if it equals to it belongs to N. So how will we do this? Okay, so our question was how to reach the green here, how to reach this green here out of the blue we have here. We have this, and we have HB normal. Okay, now because we have CD inverse belongs to N, that means CD inverse equals N1 for some N1, and because we have AB inverse belongs to N, that means AB inverse equals N2 for some N2. Okay, and here we just played with it. C equals N1 D, and then D equals C1 and inverse. Take the D inverse, and then we get that. And same thing, we played with that. A equals B and 2, that means B equal A and 2 inverse, and maybe okay, and so on. Maybe it could be easier if I could assume here, I could assume for a while here, A equals N2B. Try to do this, the solution, but using this instead of that, and see if the solution becomes shorter. Okay, but let's continue with what we have already in here. So this is B. Now take the B inverse, we got that. So we will use this for D inverse, and we will use this for B inverse. Okay, so remember, we want to show this belongs to N, so we start with it. Here we go, we started with that. Okay, now play with this multiplication. We replaced D inverse and B inverse with this thing here. This is D inverse, this is B inverse. Now if you notice what I have done here, I changed N to A inverse to A inverse N3. Why is that true? Because N A inverse equals A inverse N. Why? Because N is normal. Since N is normal, then left cassette and right cassette of N are the same using any element of the group, and A inverse is one of these elements, is an element of the group. So N A inverse equals A inverse N. So N2 A inverse equals some A inverse times some elements which we call n3 from n. Okay. Now, once we got that, I played with the associativity here. So I did not change the order of elements, but I played with associativity and rewrote it this way. Now, what happened here, I will use the equality in here. C inverse A inverse is an element of G, right? So the left coset and right coset of that element are the same. Okay, so n1 times this element C inverse A inverse must equal C inverse A inverse for some other elements in n, which is n3, say, for some n3 belongs to n. Okay, and 4 I used here, sorry, I used here and 4. Okay, so once I got that, I used associativity again, and so this and this here will give us the identity, and that will leave n4 times n3. These two elements are from n already, and n is a subgroup, so it is a closed under multiplication. Then we found that this equals this, and so it belongs to n, and therefore we are done, because this implies that AC equals BD modulo n. So it is fun to play with these things, and remember to use the normality the way we used it. I'm not sure if the proof in the book is much faster than this, maybe, but I liked to play with it the way just comes to my mind. You may play with it and find another shorter solution, and you must play with it. Please go again and play with it. Change this, or maybe you change that. You will say, okay, no, I want this to be C equals dn1. If you choose both of these together, it will give you same long as the proof here, but keep one of them, keep cn1d, keep it, and replace this, use that. So use these two things now, and I expect that will give you a shorter proof. Okay, so alternative description of normal subgroups. Given a subgroup, then you are asked to show it is normal. If you want to show the definition, it might be a very long way, because you need to compute left coset, right coset for all elements in the group G. Or if you, as we have seen in the example, if the subgroup comes out to be the center of the group, then it is normal right away. But in general, showing a subgroup is normal is done by either using 2 or 3. What do you mean by 2 or 3? The conditions in the following theorem, and it is easiest way to prove that a given subgroup is normal. So when you are asked to show that a given subgroup is normal, just go ahead and prove it satisfies 2 or satisfies 3 of the following theorem. How do you know this? How do we know this is true? Because we are going to prove it now. Now this theorem says the following are equivalent. So every condition of these is equivalent for having n to be normal. So the following are equivalent if n is a subgroup and G of G, then n is a normal subgroup of G is equivalent to any of these 4 conditions, 2, 3, 4, and 5. Okay? Now let's prove the theorem, and the way we'll do the proof, we will prove that 1 gives 2, and then we will show that 2 and 3 are equivalent. We need this. Why? Because we will prove 3 gives 4, And to prove 4, starting from 3, we want to prove 4. 3 will not be enough by itself. We need 2 to come with it. So we will prove that 2 and 3 are equivalent. Okay? We will prove that 2 gives 3 and 3 gives 2. Okay? Same thing, we will prove that 4 and 5 are equivalent. Why is that? Because once we come back to prove 1 is correct, starting from 5, we will need 4 to come with it. So we will need 4 and 5 to prove 1 is correct. And I also said we need to prove 2 and 3. We need to use 2 and 3 to prove 4 is correct. Did I say that correctly? Did I say 1? So let me see. I think I said 1 instead of 4. Let me repeat what I said. We need to use both 2 and 3 to prove 4 is correct. And we need to use 4 and 5 to prove 1 is correct. That's what I think I said, 4 instead of 1. Okay. Because in proving things are equivalent, in general, if you have 1, 2, 3, 4, 5, what you need to prove is 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and then you go back and say, okay, 5 goes to 1, and then this is the way you prove things are equivalent. But here things are different, because once we want to prove 4, we need 2 and 3 together. So we will prove 2 and 3 are equivalent, which means if I have 3 in hand, then I have also 2 in hand. And same thing, if I have 5 in hand, then I also have 4 in hand. Okay. Again, before we start the proof, this is a warning. Having A inverse capital N, A equal N, does not mean A inverse small n equals N. The same N here and the same N here is not necessarily true. But it does mean A inverse small n equals some other element from capital N. It might be the same the same as a small n or no. Okay, for some n2, and discussion we needed to work out the proof clearly, correctly. So let's work the proof. Let's assume n is normal and show that 2 is true. So I will try to do this for quick. We want to show that 1 gives 2. We want to show A inverse capital N, A belongs to N. That means we want to start with let A inverse and A belongs to this for some N belongs to capital N. Okay, we want to show this belongs to N. To do this containment, we want to show this belongs to N. Okay, oops, what I did. No. Okay. And remember, we have now N is normal, right? So now, okay, we want to prove this belongs to N. Now, A inverse N times A. How to prove this things belongs to N? Simply notice that NA belongs to capital NA, which is equals A capital N, right? Because N is normal, and that means NA equals A N1 for some N1 belongs to N. You agree with that? Now A inverse small n A equals, so we will replace this. We will have A inverse A N1. Now use associativity, and that will be N1, and that belongs to N, and then we are done. Okay, so this belongs to N. So we are done with 2. Now we will prove that 2 and 3 are equivalent. Okay, and okay, we will go from 2 to 3, but 2 says that A inverse capital N, A is contained in N, and this is for every A in the group, for every element in the group. So we will replace A inverse, I will just say it easily, we'll replace A by A inverse, right? Because in place of A we can use any element of the group. So we will have now replace here by this A, replace it by A inverse in here, and in here we will have A inverse inverse n. A inverse is contained in n. This is what 2 tells us, right? But this means A, this is A, and A inverse is contained in n, and this is 3. So we proved 3, and we are done. Now to prove 3 gives 2, we will do the same. So I will leave it to you. 3 gives 2. Now 3 says A and A inverse is contained in n. Again, replace A with A inverse, and then we get 2. So this is so quick. Now to prove from, but if it is asked, if you are asked to do that, you must write that clearly. Please read it from the book and write it your own way. Now let's prove that 3 gives 4. Okay, 4 we need to show that 3 says so we want to show this quality, but 3 gives give us one direction of this quality. We want to show this, right? 3 give us which one, which equality? Okay, now this equality is true by which part? By 2. Okay, you may say, but we're starting with 3. Okay, this is where I said once we have 3, that means we have 2, because we showed 2 and 3 are equivalent. So if you are assuming you have 3, then you can use 2. So this containment in here is true by 2. So we want the other containment. So now we want the other direction. We want to show that n is contained in A inverse n A, and that is for every element A belongs to G. To show simply A inverse n A equals n if and only if A in A inverse equals n. So this was part 4 and this was part 5. Now this shall be direct, showing this because A inverse n A equals n for every element in G, then replace A by A inverse. So simply replace this by A inverse. We get A inverse n equals A inverse here equals n, and then we are done. This is A inverse A inverse equals n. Then we get 5. Now the opposite direction is very similar. Just replace A by A inverse. Now we want to prove the last part, which is 5 gives 1. 5 says so let's write it here. 5 gives 1. 5 says A and A inverse gives n. We want this to show, use this to show that n is normal. So this is 5 and this is 1. Okay, so we want to show 5 gives 1. Okay, so if we show this, then the proof is done. So to show A is normal, we want to show that A is any element. To show that n is normal, I said A. We want to show that n A equals a n for every element in the group G. And here we have it. This is for every element in here. This statement is assumed to be true for every element in G. Now, if we have we want again the part we want, which is left to prove, is n is contained in A inverse NA. We cannot simply say multiply A from both sides. We need to choose n here, small n, and prove it belongs to this thing. This is what we want. So let's start with the small n. Let n belongs to capital N. Then write or now 3 says A inverse is contained in N. So this one is contained in N. So A inverse equals N3 for some N3 in N. Okay, so let's go and change it. A inverse, and this is N3, and this is A. Okay, now what we get, and we are done. Okay, we are done. This belongs to an inverse n A. So we got small n belongs to an to A inverse n. Small n, use since A n. Come on. يلا. Okay. A inverse equals n. عندها small n ينتمي له هنا. Then راح استبدل small n هذا ب A n1 A inverse. اوكي هذا اللي بدي اياه. لذلك NA equals راح استبدل ال n بهذا المقدار AN1 A inverse times A. Now use associativity. This is AN1 and this belongs to AN. هي بهذه البساطة. إذن NA belongs to AN وأنا اخترت NA من capital NA وهذا بيعطيني capital NA equals A capital N. الآن الاتجاه الآخر اللي هو حتى أثبت هذه الكونتينمنت راح استعمل نفس الشيء. راح استعمل hypothesis مرة أخرى. حتى أثبت هذه الكونتينمنت راح أختار element من N وأقول AN belongs to A capital N والمطلوب هنا want إنه A small n ينتمي إلى capital N times A. هذا اللي بدي إياه. مرة أخرى since n equals A inverse we have A n 5 هيك بتقول A inverse then small n هذا يساوي A equals n2 A inverse for some n 2 belongs to n. أعوضه هنا فراح يصير عندي A n equals A n. أنا بدي استعمل 4 هنا. حلو لأن قلنا 5 هي equivalent ل4. الآن بلزمني استعمل بارت 4 هنا وأقول إني بدي الانفرس يكون A inverse n A. جميل. A inverse n A. إذن هذا A inverse n A. إذن oops A times n equals A. Now replace A times replace n by this and then use associativity and the id we get that. And this belongs to an A. And now we got A small n belongs to an A. That means A capital N is contained in N capital A. And then we are done. In here I should write contained not equal. So this part here and this part here finally give this give n times a equals a times n. Finally, small techniques, but sometimes comes out of mind. Okay, and then we are done. And I believe when we need to show our last example in this theorem. Okay. خلص الوقت أميرة معاكم حق، بس أنا بدي أخلص التسجيل لأجلكم، لأن بدي الفيديو يكون موجود قطعة واحدة على اليوتيوب. فخلينا نشوف الإكزامبل هذا. نحن انتهينا هذا الإكزامبل فقط. Only this example. So this is normal subgroup. Okay. In S3 has 6 elements. So you either go and compute the left coset, right coset of every element and show they are equal, or you try to use this theorem somehow. Okay, first the only subgroup of order 3 in S3 is this subgroup. Why? If we choose another element of S3 outside this group, it will be a reflection, so the order is 2. Okay, so since the order of those of any element of those is 2, then it cannot be inside a subgroup of order 3, because by Lagrange theorem the order of an element must divide the order of the group it contains it. So this is the only subgroup of order 3, and we know that. Now choose a sigma that belongs to S3 and compute and then consider sigma inverse A sigma. You know, you have shown this is also a subgroup of G. A subgroup, our G here is S3. So this is also a subgroup, okay? And it has the same order as of A. Good. And I just have said A is the only subgroup of S3 with order 3. So I have only one subgroup in S3 of order 3, and I am saying here that this is a subgroup. It has order 3, and this is a subgroup. It has order 3, and therefore we must have that, because we only have one subgroup of order 3, and each of these subgroups has order 3. That means they are equal. And remember that the element we choose in S is any element. So that means A is normal. Okay, then we are done.